Hello students and welcome back to my channel. Today I have come to discuss questions from electrodynamics, that is complete electrostatics, current, electricity and magnetism, which were asked in the morning session of 29th January 2023 JEE mains exams. So let us continue. This is the first question. In a cuboid of dimensions this, a charge q is placed at the center of the surfaces having area of 4L square. The flux through the opposite surface to S is given by. You have to apply a trick, students. Otherwise, slightly you will be in a problem. Right. So let us draw the figure. We will be applying Gauss theorem, but with a technique. So this is a cuboid, as you can see. Two of the sides are 12 each and one of the side is L, that's edge. Two of the edges are 12 each and one is L. So there is a surface S having area 4L square. So you can take this. This is 2L and this is also 2L. So this area will be 4L square. So this we can take it as S. So a charge Q is placed at the midpoint, center of the surface S. Now let us call the face opposite to S as S dash. So this is the opposite face. So we have to calculate the flux through this. So the concept is very simple, student. Just place another identical cube on top of this. I'll mark the cube with a red color so that you understand that it is additional cube which has been placed above this, and this cube is identical to the previous, this cuboid is identical to the previous one. So this is how you place it. Now you can treat the entire body, that is the cube, as the Gaussian surface. This is the Gaussian surface, and as you know, the total flux coming out through a Gaussian surface will be charge enclosed within the Gaussian surface upon epsilon 0. This is the total flux. And since all the six faces are located symmetrical relative to the charge, so the flux intercepted by each surface, will be 1/6 of the total flux coming out. So this is the correct answer. Fourth option is the correct answer. Moving on to the next question. A point charge Q1 equal to 4 Q naught is placed at origin. Sorry. Another point charge Q2 equal to minus Q naught is placed at x equal to 12. So charge of proton is Q naught. The proton is placed on x-axis so that the electrostatic force on the proton is 0. In this situation, the position of the proton from the origin is. This is again a very simple question. So suppose this is the x-axis and this is the origin. This 4Q naught has been placed at the origin. So here you have 4Q naught, of course positive charge, and another minus Q naught charge is placed at a distance of 12 cm. So here you have minus Q naught at a distance of 12 cm on the x-axis. So we have to find the position of a third charge proton of charge Q naught, so that the force on the proton is 0, not in, it is 0. So students, now you see that this entire x-axis has been divided into 3 zones. One is to the left of 4Q naught, the other is between 4Q naught and Q naught, and the third one is to the right of minus Q naught. Okay, we have to check what will be the most suitable position for the proton so that it does not experience any force. Now suppose you keep the proton here, left hand side here, this somewhere here. Then this proton, this positive charge will repel it and this negative charge will attract it. So both the forces will be opposite. So there are chances of net force becoming zero. But there's a big but. What is that? Now this 4q naught charge, which is more in magnitude than minus q naught charge, is closer. So here the value of charge is more as well as it is closer to this point. So force due to this charge will always be more than the force due to this. So they cannot become equal. However, far you go away to the left. So there is no possibility here of the force becoming zero. Now, coming to the space between them, here somewhere you can see, due to this 4q charge, it will be repelling it because this proton is a positive charge particle and this negative charge will be attracting. You can see the forces will be directed in the same direction. Again, there is no possibility of the force becoming zero because the resultant of two force will be zero if and only if they are equal in magnitude and opposite in direction. As simple as that. So therefore, the only possibility seems to be somewhere here. So you place that Q naught charge here. This 4 Q naught will repel and this minus Q naught will attract. So this is how. So we have to find the position X. Let us take this as X. Sorry. So this distance will be X minus 12. X is in centimeters. So both the forces must balance each other. Forces must balance each other. So force due to this will be K into 4Q naught into Q naught by X square. Whereas force due to this negative charge will be K into Q naught. Students, you should not take the negative charge with the negative sign because we are just considering the magnitude. Just we have to consider the magnitude here. So, and immediately extract the square roots. So when you extract the square root, don't use plus or minus because we have already investigated the entire thing. X has to be plus. So there is no need of putting plus or minus while you extract the square roots. So kk gets cancelled, q naught gets cancelled, and so on. So you have x is equal to 24 centimeters. So 24 is the correct answer. Then moving on to the next question. In a meter bridge experiment, the balance point is obtained if the gaps are closed by 2 ohm and 3 ohm. A shunt of X ohm is added to 3 ohm resistor to shift the balance point by 22.5 cm. The value of X is. So this again is simple question, students. I'll roughly draw the meter bridge. So this is how the meter bridge looks like. Now there's a 100 centimeter long wire. So in the first gap you have 2 ohm. So there's a 2 ohm here. And the second gap has a 3 ohm resistor. So there's a 3 ohm resistor here. And the balancing point, let us say it is C. So since total length is 100 centimeters, sorry. So this ratio of this length will be in the ratio 2 is to 3. So when you divide them, the length comes out to be 40 cm and 60 cm in the ratio of 2 is to 3. Then it is given that the 3 ohm is shunted by X ohm. Shunting means connected in parallel. Remember this, whenever a wire is shunted with another wire, it means they are joined in parallel. So when you join anything in parallel, then here the resistance will decrease. So naturally the balance point will shift towards right. So in the next situation, I'll again draw the new diagram so that you understand properly. The 2 ohm remains as it is, whereas this time the effective resistance I'll take it as R, okay, and the balance point would have shifted by a distance of, it is given as 22.5. Remember 22.5, okay, 22.5. So this was already 40 and this was already 60. Okay. So we can find R. Based on this, we can find R. And once you know R, then you know R is actually the effective resistance between the 3 ohm and X ohm. So with that you can find X. So let us apply the concept of principle of Wheatstone bridge to this meter bridge. So here we have R upon 2 is equal to, this length will be 60 minus 22.5, that is 37.5, and this will be 40 plus 22.5, that is 62.5. So 37.5 is equal to 62.5. Okay, so we can remove the decimals. If we remove the decimals, we get 375 and 625. So we can cancel this with 5, 5 sevens are 35, 5 fives are 5 125s are again 25 threes are 25 fives are. So R is equal to 6 by 5 ohm, and we know R is the effective resistance between 3 and X. So we have product upon sum is equal to 6 by 5. So therefore we cancel this, 3 twos are 6. So we have 5x is equal to 6 plus 2x. So 3x is equal to 6, so x is equal to 2 ohm. So the correct answer is 2 ohm. Then moving to the x, the value of x is 2. Moving to the next question. The ratio of thermal energies in two resistors R and 3 are connected in parallel in an electric circuit is. So if the resistors are connected in parallel, that means voltage remains same. Let us take the voltage as V naught. So if R is the resistance, then the ratio of thermal energy released, in fact, we are calculating the thermal energy released per unit time. Thermal power is given by V naught square by R. So as you can see, that power varies inversely as R. So therefore, power in the R resistor upon power in the 3R resistor will be in the inverse ratio of the resistance, that is 3R is to R, that is 3 is to 1. So correct option is the first option. Then moving on to the next question. The magnitude of magnetic induction at midpoint O due to the current arrangement as shown in the figure. Sorry. You have to subdivide all the wires into different state segments. So I'll number this as 1, then this has 2, this has 3, and this has 4. As you can see, that point O lies along the axis of wire 1 and 3. So there will be no magnetic fields whatsoever due to wire 1 and due to wire 3. You are left with wires 2 and 4. As you can see, each is a semi-infinite wire. So numerically B2 and B4 will be same, which will be equal to mu 0 upon 4 pi into I upon R, where R is the distance of the point from the wire. Distance of the point from the wire, you can see it is A by 2, A by 2. So when you substitute here, we have mu 0 I upon 2 pi A. Okay. Now you can see, if you apply the proper right hand thumb rule and all, you will find that due to this wire, the magnetic field, that is B4 is actually out of the plane of the page. Similarly, B2, okay, B2 is also out of the plane of the page. So both being in the same directions, resultant can be obtained by adding them, because when vectors point in the same direction, in order to calculate the magnitude of the resultant, you need to add them. So when you add, you have to double it since both are same. So twice mu 0 I by 2 pi A. So 2 gets cancelled. You are left with the fourth option. So correct option is the fourth option. Then coming to the next question. A single current loop of wire carrying current I flowing in the anti-clockwise sense seen from negative positive z direction and lying in the xy plane is shown in figure. The plot of component of magnetic field at a distance less than the radius of the coil and on yz plane versus z coordinate looks like. So we have to understand, student, this is the point somewhere here. Okay. So we have to go on plotting the y component of magnetic field along this line. Y component of magnetic field. Now, if we can draw the lines of force, as you can see, if the current flows in this direction, then the lines of force will flow in this direction, this way. This is how the magnetic lines of force they pass through they are closed lines, you know. Magnetic lines of force are closed loops. So here you can see that the y component is practically zero because y direction is like this and the net field here at point O is actually here, it is exactly along z axis. So 0, when z is 0, b is 0. So this option gets eliminated and even this option also gets eliminated. So we are left with option 3 and 2. Now here you see on the positive z axis, somewhere here you can see positive z axis, the component of y will be in the positive y axis, positive y axis. So both have positive y axis, whereas here to the left of the origin, somewhere here you can see that the component has negative velocity, negative component of magnetic field along y axis. So negative means this, so correct option is this. And as you know, if you move away and away, practically the field intensity will reduce to zero at a far off distance. So that is third option is the correct answer. Then, coming to the next question, a certain elastic conducting material is touched with a circular lobe. It is placed with its plane perpendicular to a uniform magnetic field this much. When released, the radius of the loop starts shrinking at a constant rate of 2 centimeters per second. It should be centimeters per second. The induced EMF in the loop at an instant when the radius of the loop is this way. So this is the loop, let us say the field is perpendicular to the plane of the loop. So the magnetic flux linked at any instant will be A into B into cos 0. Remember, angle between area vector and magnetic field is 0. So area is, if you take the instantaneous radius as r, then area will be pi r square into B, cos 0 is 1. Now according to Faraday's law, the induced EMF will be minus d phi b by dt, rate of change of magnetic flux. So this will be pi b d by dt of r square. Differentiate this with respect to time t. So this will be 2 r dr by dt. I have dropped the minus sign because it is of no use for us. So therefore pi is 3.14, magnetic field is 0.8, that is I can write it as 8 by 10, twice radius at the instant radius is 10 cm, 10 cm is 1 by 10 meter, and dr by dt is given as 2 meters. You convert it into meter by dividing by 100. Okay, so this is how you get the answer. You should get the answer. Since we are asked in millivolt, remove this 1000 from here. So we have here 2 to the 4, 4 into 3.14, maybe somewhere around 13, close to 13, maybe into 8 upon 10 millivolt. I must get correct. Everything is fine. Good. So this is approximately equal to 100. Okay. So finally it is somewhere around 10 millivolt. So 10 is the answer. So next, coming on to the next question. Find the mutual inductance in the arrangement when a small circular loop of wire of radius r is placed inside a large square loop of radius of wire of side L. L is too large compared to R. The loops are coplanar and their centers coincide. Now, students, first of all, let us do one thing. Let us calculate the magnetic field at a distance, let us say A, and let us say these distances are L by 2 each. There is a current carrying wire. Okay. This is also L by 2, let us say. So here, if you apply the formula which is derived from Biot-Savart's law, then we can write magnetic field here as mu 0 by 4 pi into I upon A. A is L by 2 into, join the end points here, join it, and you have 45 degree each because this is an isosceles right angled triangle. So sine alpha plus sine beta. So sine 45 degree plus sine 45 degree. This will be, I'll take this as B dash. So this will be mu 0 I by 2 pi L into root 2, which can further be written as, or I'll keep it like this. Okay. Now, this is the situation as per the question. This is the situation. There's a big square loop and there's a small circular loop. We have to find the mutual inductance. We have to find the mutual inductance. So in order to find the mutual inductance, you have to take the primary coil in such a way that the flux through the secondary can be calculated. So here we can calculate the flux through the secondary if we choose the small circular coil as the secondary. I'll explain why. So the bigger coil has been taken as primary. So let a certain current IP be made to flow through the primary. If the magnetic flux associated with the secondary be 5s, then the coefficient of IP will give you M. This is how we calculate. This is how we calculate. So the magnetic flux linked will be, now all due to all these four portions, that is this and this, the field will be along the inside normal, inward normal. And since it's a small wire, so we can ignore the variation of magnetic field, okay, within this area, and we can assume the magnetic field to be uniform. So assuming B as the magnetic field, B into A, this is the magnetic flux total because cos 0 will be 1, okay, and that can be equated to MIP. So therefore MIP is, magnetic field is 4 times of this value because we have already calculated the field due to each side. So all the 4 sides will contribute equal magnetic field at that point. Yeah. So 4 times of this is the net magnetic field. So 4 mu 0 I root 2 upon 2 pi L into area is pi r square, pi into r square. So this is equal to, so IP gets cancelled as you can see, and finally we are left with 2 root 2 in the numerator. This 2 comes from here and root 2 is already there. 2 root 2 mu 0 pi r square by L. So correct option is the third option. This is how we find. That's all in this video, students. Thank you so much for watching. Please subscribe to my channel and hit the like button. Thank you so much.